Alright, welcome everybody. So today we're going to talk about bonding. It's our first video on this really large and important topic. You know, this topic really sort of is the basis for all of the other things that you're going to learn about chemistry this entire year. And so what we're going to, talk about today are different types of bonds, and we're going to start with ionic bonds. So before we get into ionic bonds, I want to talk to you a little bit about generally what a chemical bond is. And so when we think about a chemical bond, it's really the forces that are holding together the atoms or elements in a compound. So like, for example, I could have something like two chlorines bonded together. And so I would have my chlorine here and my chlorine here, and the two chlorines would be bonded together. This line here, which I'll highlight, represents the bond between them. And what's really happening between these chlorines is we have two nuclei that are in each chlorine atom, and then we have the electrons that are between them in the bonds. And so what we end up with is this mutual attraction for the electrons between the two nuclei. So we have this mutual attraction. Between the two nuclei and the electrons. There's also repulsion there between the electrons and between the two nuclei, so it sort of ends up balancing out, where they reach this distance called the bonding length, and those two chlorines always will have a certain length between their nuclei that corresponds to the optimal distance between them. Now you could have, where you're not really having the two nuclei sharing the electrons like this. You could have a situation where you have ions, like we could have a positive ion and a negative ion, something like Na plus and Cl minus. And here with my Na plus and my Cl minus, we have an attraction between the ions in an ionic bond. And I'll go back through this in the next slides. So why would a bond form? Well, the whole idea behind bonding is to really lower the energy of the system. If we can remove energy from a system, then what happens is it becomes more stable. And that's really a key to chemical bonding, trying to remove energy from the atoms when they're isolated compared to when they bond. And you'll see when you do reactions, a lot of times there's heat given off. The heat's given out, the compound that forms is more stable, it's less reactive. So when we draw, structures of different compounds, it's really important to know how to do something called the Lewis structure. And the Lewis structure is based on the valence electrons. And so each of the symbols for the Lewis structures is shown below. What we have here is we have the symbol, which I have as an X, and then each dot is an electron. So if you are an element with one valence electron, you would have Li and then a dot. If you were something with two valence electrons, you would have the two valence electrons like this. If you were three valence electrons, like aluminum, then you would have three dots. If you were four valence electrons, like carbon, you would have four dots. If you were five, like nitrogen, you would have five dots. Oxygen, 6 dots. Fluorine, 7 dots. And finally, xenon, 8 dots. Now, it's no accident where I put the dots. They're supposed to represent the s orbitals and the p orbitals. So that's why I drew the dots where I drew them. Now, the first type of specific bond that we're going to talk about is an ionic bond. And just like with any type of bond, ionic and covalent, you've heard those terms before, the idea behind them is to form something called an octet. And this is called the Octet Rule. And this is where the atoms or the ions, they're going to either lose, gain, or share electrons until they get 8 valence electrons. Oct means 8, octet is 8 electrons. There's actually some exceptions to this, but we'll get into that later, but for now we'll follow this rule. So the first type of bond, like I said, that I'd like to talk to you about is an ionic bond. You have to know some of these details, so you should know what types of elements are present in the ionic bond, and you should know that this is a metal and a non-metal part. Hopefully you've started memorizing some of your polyatomic ions. you can see that those are usually groups of nonmetals. Those correspond to the nonmetal part. What changes occur when in these elements that cause them to bond together? Well, the metal and the nonmetal both have to undergo changes. The metal is going to lose electrons, and the nonmetal, not no metal, the nonmetal is going to gain electrons. What happens is when the nonmetal gains electrons, it becomes a negative ion, and the metal becomes a positive ion. These end up being attracted to each other. So they attract each other and they form this stable interaction. So when the compound's formed from its elements, you end up being more stable. And what I mean by stability is, as I mentioned before, lower energy. This lower energy comes from this huge attraction that happens between the positive and the negative ions. So you'll have a positive ion and a negative ion, positive ion and a negative ion. This is in 3 dimensions, in all directions in 3 dimensions, and so you end up with something called a lattice. A regularly repeating pattern. So, what forces are holding these together? Well, these positives and negatives that I drew up here, these actually have a name. It's called electrostatic. So these electrostatic forces are opposite charges, positive, negative, holding the ions together in an ionic compound. How strong are these forces? They're really strong. And what you'll see from ionic compounds, one big key factor is that they are hard and that they also have very high melting points. Not that I'm advocating that you do this, but if you were to go and take some salt, some NaCl from your kitchen, and you were to put it in a small pot and you try and heat it up on the stove to make liquid salt, molten salt they call it, you'd have a really hard time doing that. It would be really difficult to accomplish. That's because even with that hot stove, you wouldn't have enough heat to actually melt those down. You need about 900 degrees Celsius in order to heat and melt the salt solid into liquid salt. Now, let's take a look at, something I can't do in class because it's too dangerous, but the formation of salt, NaCl. And you'll notice I keep saying the term salt. Salt is almost synonymous with ionic. We'll go back and forth and we'll talk about that. We'll be like salt, ionic salt. That's how we will say those two terms. I use them interchangeably all the time. So here's my, ionic compounds forming. I have my chlorine gas that they show up here, and I have my sodium solid metal here. When I put them together, what happens is this fireball emerges, and you end up forming sodium chloride crystals that will be at the bottom of the test tube here. Look at all this light being given off. This is fire right here. That's all that energy being released when you form a bond. And in general, I like this acronym called BARF, B-A-R-F, and it stands for break, absorb, release, form. So when you break a bond, you absorb energy, and when you form a bond, you release energy, B-A-R-F. Now let's talk a little bit about ionic compounds, how to represent them. So we could just write the formula for them, and I haven't really taught you how to write formulas. We're going to do that next chapter. But take something like NaCl. So I would have my sodium, and I would have my chlorine. So what makes it NaCl? Why is it Na and one Na and one Cl? Why isn't it more than one or the other? And how do I show this with something called a Lewis structure? Well, let's look at sodium over here. It has 1 valence electron. And here's chlorine. It has 7 valence electrons. And you could do different colors or X's and dots if you want. And so what happens is this sodium, it is going to lose its electron to chlorine. Remember the details back from just a few days ago, the periodic table. We talked about sodium having low ionization energy, low electronegativity, large radius. That makes sodium lose its electron, and chlorine gain that electron. So what we end up having here is we end up having Na as a positive ion. Notice I put brackets around it. we have chlorine gaining that electron. 1, 2, 3, 4, 5, 6, 7, 8. Put brackets around it and show that it's a negative ion. You could put the positive or negative in or outside of the bracket, doesn't really matter. So just to be consistent here, I'll move this out so that you can see that I'm consistent. But now we have a Lewis structure, really, really straightforward. What if I had something where it wasn't 1-to-1 like this? So what if I had like Ca and Cl2? So if I have a compound like this, I'm going to have my Ca with my 2 valence electrons, and I'm going to have my Cl with its 7 valence electrons. Well, Ca can give 1 electron to chlorine. That will have an octet. But there's another chlorine needed, and that's where that 2 comes in. So another chlorine here will take this electron, and what we're left with is we're left with Ca being +2. It lost its 2 electrons. And then we have our 2 chlorides, and they're both minus because each one gained an electron. Now, this is sort of a pain to do each time, show the electrons. If it helps you, great. But look at what I did here, in short. What I did here was, 1, I wrote the symbol of the metal, and then I wrote its charge. And then I wrote the symbol of the nonmetal with the 8 dots to represent the electrons with its charge. Notice I use brackets for both. Now, how do I know the charges? If I'm going to do this, how do I know the charges? And I'll show you how you know the charges. When we have ionic compounds, the charges are kind of set, and I'll show you what they are right now. Let me just add a page in right here real quick and show you this as our ending, and then I'll give you some practice to try. So let's say that I were to have something in group 1. Group 1 will always be +1. Group 2 is always +2. Group 3, or 13 I should say, is +3. Group 14 is -4, 15 -3, 16 -2, 17 -1. So here are my charges for each of these elements. So something in group 17 like fluorine, that would be like F-. Something in group 16 like sulfur would be S-2. Group 15 nitrogen or nitride would be -3, carbon -4, aluminum +3. Group 2, magnesium +2, and group 1, sodium +1. Any element in those groups will follow will follow that pattern. So you can use that for your charges and take a shortcut. Let me finish with one, and then I'm going to stop. So let's try something like Al2O3. So I can use the groups now to get through this. If I look for aluminum, it's +3. It's in group 13. And oxygen is -2. And now I follow the rules. I write the symbol of the metal. I put a 2 in front because there's 2 of them. I put its charge. I write the symbol of the nonmetal. I put the 8 dots around it. I give it the brackets. I show that there's 3 of them, and I put its charge because it's in group 16. I'm done. Easy to do the Lewis structure without going through transferring all the dots. So try a couple of them. Why don't you try something like, let's try like rubidium, oops, it should be an R, rubidium oxide. Let's try calcium phosphide. And let's try, something like aluminum chloride. So try these 3. I want you to draw the Lewis structures for each of them. Show the brackets, the charges, the numbers. All right, thanks for watching, and we'll discuss this when we see each other in class. All right, thanks so much.